allow me to walk you through the research we have conducted over the past 1.5 to 2 years on the use of large language models in digital education. Within our DLR-funded mandate, we have been fortunate to explore these technologies comprehensively, experiment with their capabilities, and assess their potential impact. Today, I would like to share some key insights, and perhaps more importantly, to issue an urgent call to engage with these developments. As you will see, this represents an extraordinary opportunity for all of us in the near future. I will present a number of examples, tools, and perspectives with the intention of sparking questions and discussions. Let us begin by briefly considering how educational content production has evolved. When we first started nearly 15 years ago, our primary focus was the creation of massive sets of PowerPoint slides. To put this in perspective, assembling just one complete set of training resources on radar remote sensing required almost 2 years of effort. It was a painstaking process involving extensive research, script drafting, graphic design, and review cycles. This approach, while thorough, was inherently slow. The next stage, which represents the present day, involved the production of massive open online courses. For example, on the left of this slide, you can see our Echoes in Space course, and on the right, some images of our team traveling to Edinburgh to record interviews with experts such as Professor Ian Woodhouse. Once again, the effort required was substantial. A professional camera crew, travel logistics, post-production, and more. Producing a single high-quality course in this manner took approximately 1 year. These examples illustrate that, historically, creating robust digital education content has been slow, resource-intensive, and limited in scalability. However, the landscape is now changing rapidly. Many of you are already using large language models, perhaps to answer questions in your daily life or to support professional tasks. Our goal was to systematically analyze how these models can be applied in e-learning and digital education. We structured our findings into 2 main categories. The first category is media conversion. Large language models are exceptionally strong at transforming one form of text into another. To illustrate, I can ask a model to produce a narration script for an online course on radar frequency bands, and it will instantly generate a polished draft that I can use in my videos. Conversely, I can instruct the model to distill that same text into a single, concise statement. This means that today, we can convert text at will, summarizing, expanding, translating, or reformatting it as needed. Text-based transformation is the most mature and reliable application of these technologies. A slightly more advanced example is the conversion of text to images. To demonstrate this, I conducted a small experiment. Here, you see an original infographic from the NASA program illustrating radar frequency bands. My objective was to reproduce this graphic using large language models. At first, I provided a simple prompt. Make an infographic on radar frequency bands. The resulting image was, technically speaking, a graphic. It contained some information, but it was neither structured nor truly useful. To improve the output, I crafted a much more detailed prompt, specifying colors, fonts, label positions, numeric values, and design elements with precision. Even so, for quite some time, the results remained unsatisfactory, often visually inconsistent, lacking alignment, and failing to capture essential details. This was the state of affairs until very recently, with the release of the most current image generation models, providing that same detailed prompt now yields an output that is dramatically closer to the reference graphic. To be clear, there are still issues. For instance, the spectrum in the upper corner was rendered incorrectly, and I was unable to adjust the modulation of the sine curve to match the frequency bands precisely. However, the improvement is striking. It demonstrates that we are approaching the point where high-quality, customized educational visuals can be produced rapidly and at scale. The final step will be for these models not merely to return a static image, but a layered, editable file, so that individual components can be refined without starting over. This small experiment underscores just how quickly progress is accelerating. Let us take this a step further. Rather than stopping at a static infographic, what if we want to produce a complete video? Using the narration script generated earlier, I tested an AI video generation tool.
Radar bands are specific frequency ranges within the electromagnetic spectrum used by radar systems for various applications, including weather monitoring, air traffic control, and speed detection. These bands are categorized by letter designations like X, C, L, etc., which correspond to specific frequency ranges and have evolved over time.
What you see here is not a real person. It is an AI avatar reciting the text. This is precisely the approach we employed for a best practices course on e-learning. Using this method, we created more than 60 videos, each recorded by a synthetic presenter. Instead of taking days or weeks, the entire process now requires only minutes. Moreover, if I prefer a different presenter, I can simply select another avatar. There is a library of professional avatars to choose from. If necessary, I can even create a fully cloned version of myself, complete with synthetic voice, so that learners experience the content in a more personal and familiar way. This capability allows us to tailor educational content to different regions and cultures by presenting the same material in the style and voice that best resonates with the intended audience. These are remarkable advances in media conversion. Now let us turn to advanced learner interactions. The most basic interaction involves a learner asking a question and the model responding. While this is already powerful, it can be enhanced through a process called retrieval-augmented generation, or RAG. In this approach, when a learner submits a query, the model first retrieves relevant information from a trusted knowledge database, such as Earth observation case studies or mission archives, and then incorporates that data into its response. This process dramatically reduces the risk of hallucination and ensures that learners receive accurate, verifiable information. We have already implemented this architecture in the GDA Knowledge Platform, which, to my knowledge, was the first production-ready Earth observation chatbot. From here, we can go even further by introducing reasoning models. A reasoning model can retrieve initial evidence, analyze and reflect on it, generate follow-up queries, retrieve additional material, and only then compose a final, well-founded answer. This iterative process of retrieval and reasoning is precisely how OpenAI's deep research mode operates internally. What does this mean for us, practically? Perhaps the most impactful application is automated content creation and translation. For example, I can submit a request to generate a learning resource, an article, an image, a narrated video, or a combination. And the model will return the content within moments. If the content needs to be localized, translation can be performed automatically. This is especially important because, as many of you know, we regularly receive requests for courses in additional languages. We now have the tools to deliver these localized experiences with a fraction of the time and effort previously required. To support this vision, we have developed an ecosystem called Remote Sensei. This platform enables the creation of LLM-based learning experiences, including chatbots, adaptive learning paths, and on-demand content generation. We plan to further develop these tools and provide them to the community. Additionally, we can build highly specific applications tailored to your particular needs. If this is of interest to you, I encourage you to reach out so we can explore the possibilities together. At this point, some educators express a concern that these technologies will eventually make us obsolete. Others worry that any infrastructure we build now will become outdated within a year. These are valid concerns. However, there is a clear path forward. Across our network, we already have a vast collection of learning materials, ebooks, videos, infographics, interactive simulations, and more. My proposal is to standardize the description of all these materials using existing learning object metadata standards. By doing so, we can create a shared collaborative repository that is structured, searchable, and machine-readable. This would enable effortless localization of content into any language, seamless conversion across different media formats, and truly personalized learning experiences, tailored to the needs and preferences of individual learners. Whether they prefer videos, podcasts, text, or interactive modules. This repository would also ensure that our collective knowledge is ready to be leveraged by whatever advanced technologies emerge in the years to come. To summarize, there is an urgent need to build LLM literacy among educators and to build capacity in this area. Localization, adaptation, and personalization of existing content are already possible. We can create advanced learning experiences, implement workflow automations for on-demand content, and streamline routine tasks in a way that saves significant time and resources. I believe the time is now to establish this centralized repository for learning objects, a modern, strategic initiative that can serve as a focal point for WGCapD in the coming years. Thank you very much for your attention. If you have any questions or wish to discuss these ideas further, please do not hesitate to get in touch.